a little bit that R naught is just not trivial, and that was what we can do. And then we really don't understand about VKL at all. It's really that. So what we really needed to do after some point was that you know, this is perturbation idea. How did we come up with that? Was through the inversion, right? So it's like we look at the cell problem first, and then yeah, maybe I can say it a little bit in the ad hoc way. Let me go all the way down here so that I'm not messing around with my notation. So we first start with A naught of y is and I honestly believe that there can be better proof and more constructive ideas understanding this thing deeply, and we only have that R naught of y1 is not 0. And then we were thinking in an ad hoc way of surely, I mean, this is a natural thing to do, you know, A naught of y with A naught is nearly 1. This is natural, just perturbations. But we really don't know what is the solution to the ergodic problem. So so what we did was that we tried to write out this ergodic problem in our way, right? Write like this. So plus A2 of y, y2 equals to A1 of y or whatever, plus A1 bar, something like that. And then and then we do it in the ad hoc or reverse way, because from here, you know, like we can just write out A1 of y, right? You know, because this is A1 of y, Vy1 y1 plus A1 of y, alpha y, Vy2 equals to
A1.
yeah, plus A1 of y equals to A1 bar. And then so it suggests us that we can try to start with A1 of y equals to A1 bar over Vy1 y1 plus alpha y Vy2 plus 1 or something. And then because of this, you know, it's now suggests that okay, we need to choose those to be small, and then we can choose them freely. And it turns out that there can be many choices, but one of the choices is just to choose V to be exactly related to R naught of Y1. So it's ad hoc, and it's
which helps in the later step when you check the CIJ.
yes, it might be not constructive. You know?
So another question actually related to what you just said. You do use the uniqueness of the cell problems, so that once you get this pair of V and A1 bar, you know that it's a unique one. This uniqueness statement for the cell problem, it is so for different KL, the uniqueness is independent or it's interval. My questions. So you got what my question, right?
Yes, a good point. I don't know. I mean, so what we do here is that, for example, when we do it like this, we only understand the problem for A1 bar, right?
Yeah, A bar 1 1 actually.
Yes.
Right.
So I mean, so in this case, the homogenized matrix, you know, I'm changing my notions a little bit. So you know, we only have this, right? And then clearly there are other cell problems, and then we don't understand the other problems most of the time.
But my question is to say that this V and this A1 bar is a unique one. You need to also address the cell problem of other K and L, right? So like you do prove that A bar has to be of the form you just write, and with this V and with those A bar 2 1 2 and A bar 2 1 equal to 0, and A bar 2 2 equals to some constants, you have a solution to the cell problem. I mean, you need to solve the full system of cell problems for all of the KL, not just for one, right?
So yes and no. So of course we have this the uniqueness for all the cell problem KL, and
Independently.
yes, independently.
Okay, okay. That's my question. Okay.
Yeah. For here, you know, I'm kind of also sort of like I'm also trying to avoid the other problems, because I only designed it in such a way that I can solve the one cell problem.
Okay. Okay. Yes. Yeah. If it's independent, just one of them is enough.
Yes, exactly. So they are independent, but understanding the other problems for this choice is really hard. So I choose it so that I understand only the one problem, you know. But anyway, so we can say for sure that this proof is non-constructive, and I myself believe that there should be better proofs and better understanding. You know, and I actually I tell you the ad hoc ways of how we do it. You know, it's nice, and I believe that there's better way. And
very beautiful.
okay, so thanks a lot. So let me go a bit quicker now. I'm sorry if I'm going a little bit slow and again mismatching between the left and the right. But now I have presented you the key component. I can go a bit quicker. I'll just draw certain diagrams on the right. So now we're gonna prove the theorem, right? So the theorem says that the set of C-bat matrices is open. So this have been checked and dense, right? So to prove it's dense, then again, we got these motivations from genericity from dynamical systems or other fields. Proving is being done is really important because it tells us that if you start with any good matrix, even if you just perturb it a little bit, it's sort of nearly becoming a bad matrix. So the idea we do is that we start with A naught, which is C good. Okay. Then the goal is to find a nearby matrix which is C bad. Okay, and then the proof consists of two steps. I cannot go directly from C good to C bad matrix, but then from A naught I will try to find a nearby of distance delta over 2 a matrix A1. Okay, A1 is not necessarily C bad, but A1 nearby, such that for A1 I have A1 ij y r1 of y in yi is going to be not zero for some j. Okay, so that's the first step. So the first step is sort of addressing this problem first, that having something is not zero first, because you remember if this is always zero, then it's always a C-good matrix, right? So from a C-good matrix, I have to sort of mess around a little bit to make it bad. Okay, and then from this A1, once I have this A1, I'm going to go in a distance delta over 2 to some A, which is C bad. Okay, so that's sort of the diagram, that how we do it. Okay, so let's start. So exactly that's step one I wrote here. I find A1 nearby so that I have at least in one of the row or column, whatever, that I have it's not zero. Okay. Of course, for the starting matrix A, if if this is not zero, I'm sorry, I think I made a typo here. If this is not zero, So for the starting matrix A naught, even though if it's C good, right? But if it's not 0 for some fixed J, then I can just simply choose A1 to be A naught and I'm done, right? Okay. So therefore I can assume that for the original matrix, for any row J, that I have always that A0, YJ, A0, IJY are not Y differentiated in YI is always 0. Okay. And then the idea to get A1 is very simple. So if this is the case, so let's say that I have A naught and R naught is the invariant measures corresponding to A naught. Okay. YI is always 0 for all J. And again, I mean, let me recall that when I write like this is repeated in YI. Okay. Then the idea is to design A1 is very simple. You just take A naught and you perturb it a little bit. Okay, so you just take A naught and then you just put everything is 0, 0, 0 here. You make it to be delta C of Y1 plus Y2 over R naught of Y and minus delta C Y1 plus Y2 R naught of Y. So essentially what you do is that you just perturb the first two terms in the diagonal. Right? Change it a little bit, mess around a little bit to mess up the structures of being too nice, being, you know, too nice with the invariant measures. What is really beautiful when I mess up with the, you know, this is perturbation, right? When I messed up with the A1 in the diagonal terms like this is that I want to keep the invariant measures to be the same. Okay, you know, because otherwise, as I said, I really don't know how to deal with the invariant measures. You know, many people I know, we have tried a lot and it's really hard to understand the invariant measures deeply. So I want to keep the same invariant measures. That's the message. And clearly you see that we do perturbation in such a way that we divide by R naught, right? So if I multiply with R naught and differentiate it twice, I have two terms cancel out. So therefore it's the same, so it's 0. Okay, so same invariant measures. I'm sorry, my way of writing this is not good. Yeah, let me try to change it. Let me try to write in a better way. This A1, because I don't like it like this. Okay, so maybe let me write like this. It's A1 1 plus delta C of Y1 plus Y2 over R naught. A2 2 minus delta C Y1 plus Y2 over R naught. You know, we divide by R naught so that when we multiply with R naught back, it's cancel out and everything else is the same. Same here. And here, down here. Okay. We keep other terms of the same. Okay. And furthermore, because of this little perturbation, right, we mess up the structure in one row, one column, whatever you call it. So indeed, once we mess up with these structures, I can just compute in the first row, right? So A1 of I1 Y, R1 of Y, YI, right? So it's the same for A naught. So it's A naught, I1 Y, R naught of Y, YI, except that I messed up with the first term with this new coefficient, right? So I messed it up a little bit. So therefore I should have plus delta C prime of Y1 Y plus Y2 here, right? And this is not 0. Okay, so I'm successful in messing up a little bit and I have done with the first step, right? So I have been able to go from A naught to A1. And for A1, I can assume now by changing the rows and whatever is that relabeling that I can assume that for A1, I have that A1 of I1 Y, R1 of Y differentiate in YI is not 0. Okay. So for A1, we have, and you can see that it's exactly now the same like the earlier proof we did, right? For the earlier proof we did is that the This is more general, of course, but kind of the same. Let me recall the earlier proof here, and then so that I can go quicker. So you see that in the earlier proof, when I proved that the set of C-bat matrices is not empty, I needed to prove that R0 of Y1 is not 0, right? That's the first step, and then we base upon that to construct it. And now, because for the general case, it's a bit more complex, not just R0 of Y1, but this whole thing, but it's sort of the same. Okay, so I'm gonna go quickly now. You can check the calculations, believe me. I let phi is S times this with S small, and define gamma Y to be exactly 1 over this complicated term. That's by design, so that I know how to solve the cell problem nicely. Okay, so the same here, you let phi Y is S times this thing, right? For S very small. Okay, and then you let gamma of Y is exactly 1 over this thing. And as I showed you the ad hoc computation earlier, it's done by design. I1 IY phi YY IYJY, and this is close to 1. And also same answer to the question that Sun Van asked earlier. I needed a lot of smoothness here. All this construction doesn't hold if I have less smoothness. Okay, right, because I have to differentiate things like crazy. Anyhow, so then I have AY. I can define AY is a little perturbation of A1, right? So I have from A0, I can perturb it a little bit to have A1. And then from A1, I can design A to be just gamma of Y times A1. For gamma is close to 1. So it's another perturbations, and I'm good to go. Okay, same idea. So for that, you can see again quickly that R of Y, the invariant measures is R1 over gamma Y, nicely. So that's the idea that of multiplying a matrix with sort of a scalar functions, then I can sort of keep the structure of the invariant measures in a way that I can control. And furthermore, so this is about Wenja question. For V11 being 1,1 corrector for I1, I only care about this one. The other things are independent, but it's hard to control. So V11 being the solution to this cell problem, I have this, and for the phi, I have this. Is equal to 1. Again, don't worry about the computations, but then you can combine the two. You can let Vy equals to V11 of Y plus A11 bar times phi of Y. So again, you design gamma of Y, right? So gamma is designed through V, and then you let Vy equals to V11 of Y plus A11 bar of phi Y, and phi Y is this function already defined earlier, right? And you can check quickly is that minus Aij Y Vyi Yj of Y minus A11 Y equals to A11 bar 1, whatever. So we have designed by hand exactly this corrector of the cell problem, really by hand, right? And then finally, we can plug in to compute the coefficient, and that leads to the conclusion, right? So let's compute. C111 equals to integral. I'm sorry, there are a lot of indices. Then I1 I1 of Y Ry Vyi dx dy, right? So this equals to integral in Tn I1 of Y Ry. So V is written as V11 Y plus A11 bar phi Y I Y dy, right? So the first thing is this one, right? And that one corresponding to C11 of A1. So I'm just writing as C111 of A1. Again, if this were not 0, then I'm done already, right? So I can assume that it's 0 to start with. And for the other terms, then what is remarkable is that for the other term is going in the same gap, right? So it's minus the ai1y ry differentiate in yi phi y dy a11 out here constant. And if you recall, what is this term, right? This thing is nothing but again, remember that we chose phi to be exactly that term. So I would have this as minus a11 s integral in the torus. So exactly ai1y ry yi all square dy. And this is surely greater than 0 by design, right? So because by our choice, we chose A1 so that that row, I mean, it gives us the non-zero value, and then we design the cell problem based upon that. And that gives us that we have the result, which is that I have the set of CBAT matrices is open and dense. And this is a theoretical result, right? It confirms to us that most likely, if we do numerics or we choose randomly without sort of without our mindset of choosing something symmetric. So if we choose something randomly, then most likely we would have a CBAT matrix, and it confirms something that that it was not known earlier, that in such a case, the optimal rates of convergence should only be O epsilon. Okay. So what I should say is that so the design in the proof was ad hoc. So it was that what we want, and then we designed it in such a way, and we took advantages of certain properties of invariant measures that we know. And I think that some deeper understandings are needed. We really need to understand them better. And I would tell you why, because, it really related to a groundbreaking paper of Avellaneda and Lin earlier. I believe that what we understand on this matter of C-good and C-bad matrices quite minimal at this moment. Okay. So that was that. And honestly, in the paper with Sao Chen Guo and Yifeng Yu, we didn't know any explicit C-bad matrix. Okay? So by the time that we wrote the paper, we were aware of a very interesting paper. I'll also mention it down there, of the Oxford group by Yves Katebosch, Timo Sprackler, and Andre Sully. It's a very interesting paper. And then we got in touch with the group, and Timo Sprackler was a grad student there, and we discussed a little bit, and it turns out that we share common interest, and then we discuss. And I have never met Timo in person or even on video chat. We only communicated by emails and stuff like that, and we decided to work together in one project, and it leads to some interesting results that I'm about to describe. So the first thing was that, why is this so abstract? Can we design a good CBAT matrix? And it turns out that yes, we can design. So this is what Timo Sprackler did. So this is in the paper of Sprackler, myself. The idea is, I'm telling you, you can check it. The computation is not too hard. The idea is that you start with RY. So you start with a rather complicated invariant measures. Okay. So you design an invariant measures first, and you see that it's quite convoluted, right? It's not separated in Y1 or Y2. It's quite convoluted between Y1 and Y2. And then you define a matrix A. So ay here can be thought of as 1 over ry, a naught of y. Okay, so you normalize it by the 1 over the invariant measures, and you define the matrix ay to be, you know, exactly diagonal. Okay, so if you design it this way, then A is CBAT. And, you know, as I said, Timo computed and, you know, in a very smart way to design this matrix that is CBAT. You know, so this is a great demonstration of saying that, you know, you come to the problem rather fresh and then having ideas, and you just do it by yourself. You find examples or something interesting. And I'm always a big fan of simple but important examples. The reason why this example, I'm not doing the computations here. I wrote it here. You can check me, and also it can be found in the paper. Is that this explicit example helps us to do numerics and confirm a lot of results theoretically. And I believe that for non-divergent form, if people do numerics, they, you know, so I believe that this example can be used as sort of a threshold or a what did I say? I forgot. So this example now, because I talked a lot, so I forgot what I wanted to say. So yeah, this example can be used as a benchmark test for certain results when people want to check whether things go well or not, because this is for CBAT matrix. Okay, so so this explicit example can be used as a benchmark test. Why is it good? It's good because not only we know the invariant measures, but also we know it's CBAT. And knowing invariant measures is very important because in this paper of Kadebosh, Spraguler, Sully, and then later on in our paper by Spraguler and Trapp, what we use was use of not finite difference, but we you know, finite element method. And to use finite element method, it's really important to know the invariant measures. I'll explain why. And this confirms that all the known rates, I'll explain a bit better later, are optimal. Okay, so that's why it's really important. Okay, so I'm being a bit vague now because I think I only have like 20-30 minutes, so I'm trying to be a bit quicker here to go to some further points. So I'm skipping the computation here, but you can check it, and it's a very interesting example. So at least if you ask me to design some example by myself, it's not easy, because you see that this example is quite twisted already. You know, you need to design first the invariant measures and mess around. If we don't know the invariant measures, then it's not easy. Okay. So the next question, question number 6. So I have intentionally give you a list of questions here because I believe that those questions, at least, you know, are simple yet quite interesting and important to pursue. Why is it important for W1P and W2P rates? Because as I said, you know, earlier there were finite difference schemes done by other groups. We cited in the papers. You know, now I talk a lot, so I forgot those references. So forgive me. But if we do finite elements, then I think this point I also discussed with Wanja quite a while ago. Also in divergent form, typically people do finite elements, then well, then we shouldn't measure in L infinity norm. So if we do finite elements, then measuring in LP, W1P and W2P norms are more natural. And that's why, you know, the questions on measuring the rates in W1P and W2P are important. Okay. So maybe let me say this. So this is important. In light of the finite element method, and also very important in divergent form, right? I mean, so far I haven't talked anything about divergent form. It's a huge field, amazing set of important results, you know, from periodic to almost periodic to random setting. You know, it's just remarkable. But again, I'm just focusing a little bit here on that here. So let me tell you the known results. The known results was done, as I said, in the paper by Capdebaugh, Sprackler, and Sully, was that they proved that the W2P rate is epsilon to the 1 over P. Okay, so to measure the Hessian, you really need to subtract the correctors. If you don't subtract the correctors, you cannot capture the oscillation of the Hessian. So what I write here is in a shortcut way. I'll expand it out for you. W2P is less than or equals to C epsilon to the 1 over P. And this one can be expanded out to be U epsilon X minus UX minus epsilon VKL X over epsilon UXK XLX, right? That's just my notations. I shortcut earlier. Okay, that's exactly that. So this was done last year or so, I guess. So naturally the question is it rate optimal, right? And also what's the missing W1P rate? So with Timo Sprackler, we can prove that the W1P rate is epsilon and is optimal. Okay, and furthermore, when you try to measure the W1P, that you subtract further the first order and the second order terms in the expansions, then you have the rate is epsilon to the 1 plus 1 over P. Okay, so you have a better rate. So W1P rate is O epsilon and is optimal. And if you subtract the correction terms, then you have you know, you have a better rate, right? Okay, and furthermore, what is really interesting is that by using the benchmark matrix, CBAT matrix to do testing, Timo can also verify that all the rates we have, like epsilon to the 1 over P, epsilon to the 1 plus 1 over P, are all optimal numerically. Okay, so that's why they're really interesting. Okay, so so in the last 20 minutes, let me brief through this and then tell you a key important point that we needed to use in the proof. I will not have time to tell you everything, but I hope that with this you can, you know, go through the proof if you are interested in rather quickly. So let me just tell you very quickly what we needed to do, right? So earlier in the proof last time that I defined this function UX. I mean, this was also known classically, not just what I did. I mean, this started from the books and also the papers by Enquist and Suganidis, that you can define these functions and you can try to compute what's happening, right? What's the problem here is that once you define these functions, you introduce error on the boundary, right? So you have phi epsilon x equals to g of x plus some errors on the boundary. And what is problematic is that this is the error term you introduce on the boundary, and when you do integration and stuff like that, you need to capture that error, right? Because the error can be big if you take the Hessian and stuff like that. So that's exactly leads us to the so we need to capture this error on the boundary, and this leads to the so-called boundary corrector. We are not doing homogenizations for the boundary correctors here, but we are doing bounds for the boundary correctors, and then the boundary corrector correspond to this problem. And theta epsilon equals to exactly this thing on the boundary, right? So that's really complicated. It's not easy at all, right? That crazy behavior on the boundary. Furthermore, V is something I don't know. I mean, that's why it's problematic, right? So one of the key element of the analysis is that we need to prove this lemma that the W1P of the theta is less than epsilon to the 1 over P. Again, for those of you who have deal with homogenization of the boundary correctors or capture the boundary correctors, this is natural. If it's not, then you can just think that, you know, I need to capture this theta that corrects the, you know, I add something, I mess up the boundary, and then I have to correct it, okay? So here's the key idea, how we do the proof. We use a black box from Avellaneda and Lin. So this is we use the very important tool from the, you know, very famous paper of series of paper, Avellaneda and Lin. This series of paper is around 1989, 1990. It's very influential series of paper. And what is interesting here is that although earlier I told you that we try to avoid writing the non-divergent problems to divergent form problem, it turns out that in this case we need to do so. And this is a very important device that Avellaneda and Lin introduced, that we can use invariant measures. We can make non-divergent form into divergent form. But this is not easy, okay? And also the divergent form operator is very obscure. It's not clear, but to get the estimate is enough. By the way, this estimate we give examples in our paper with Timo is that this estimate is essentially optimal. So what is really important is that we get some estimate for the boundary corrector, right? But what is really important is that we show that this estimate is essentially optimal. Okay, so here's my goal, that, you know, the last piece of key ideas I want to give you is this idea of Avellaneda and Lin. Okay, so what do? We start with this equation, right? Aij x over epsilon theta epsilon xi xj equals to 0, right? That's the equation minus. So what I do is I just multiply with the invariant measures, right? R of x over epsilon, I put it here. Okay. So I multiply with the invariant measures, and now I'm messing around. I'm going to try to make this into divergent form, okay? But it's not easy, right? So so let me try to mess it around, try to make it into divergent form. So Aij x over epsilon, R x over epsilon, theta epsilon xj x xi right? I'm just trying to put it in divergent form. This is not, right? So I have something popping out, and last time I explained that something popping out is dangerous. So it's aij x over epsilon, r x over epsilon, xi theta epsilon xj equals to 0. And what I'm highlighting now here, the second term here is dangerous, right? It's not clear. So we need to handle it. And what is beautiful from the Avellaneda and Lin paper is that they say that it's possible if you add a skew symmetric matrix. So, okay. How did they do it? So clearly we need to handle this. We need to take care of this, right? Okay. So what they did was that they defined bj of y equals to exactly this thing, right? So minus aij of y, ry, yi. Okay. So that's the terms that appear here, right? And do you recall this is exactly the term that occurs earlier when we try to analyze the C good and C bad matrices, right? So, you know, it's there naturally. Okay. And earlier we say that if Bj is 0, then the matrix is good. And clearly, if it's 0, then it helps us to transform between divergent form and non-divergent form easily. But most of the cases, it's not 0. Okay. So Bj is this, and then clearly that if you compute the divergence of Bj of B, I mean B is created by B1 up to Bn, right? So divergence of B is just Bj Yj is equal to 0, right? Because this is exactly minus aij ry yi yj, right? That's equal to 0 because r is the invariant measures. So you have the divergence is 0. Now, again, from here, what Avellaneda and Lin did is that they let phi j to be the solution to this Laplace equation. So from Bj, you solve a Laplace equation. So it's really abstract, right? You know, it's another layer of complications. So it has a solutions because the integral of Bj is 0, right? So integral into torus of Bj dy is 0 because it's you know, it's the derivative in yi. So it has a solution phi, and then they define Tij to be a skew symmetric matrix. So Tij is phi j yi minus phi I yj. Very beautiful. So you have Tij is equals to minus Tji, skew symmetric. Remarkable. Okay. And then you can see, you can compute that Tij in yi is equal to Bj. That's clear. And then we are done. Avellaneda and Lin define a tilde of ij is aij ry plus Tij. So Tij is a skew symmetric that takes care of this second terms here. Take care of this second term here, right? You know, so I'm just plugging in and do the computations for you. You have these terms here is just a normal term. You have these terms here is exactly that, and you differentiate. You have this equals to Tij differentiate xi, right? So this red term match this term and this terms matches. These two matches, right? And you have one term in addition, these terms, Tij theta epsilon xi xj. But because Tij is skew symmetric, this one goes away. It's really beautiful. I mean, it's remarkable, right? T has to be really skew symmetric, so that is the case. Okay. then once you can do it, you can transform the problem from non-divergent form to divergent form. So you have this problem in divergent form. Again, I tutor IJ is very abstract. But for here, I'm not doing something complicated. I just need something called uniform estimate. This is a very important estimate for people to do quantitative homogenizations. Is that okay? So what I have here is that a tutor is not even symmetric, right? But it's not a problem. A IJ tutor is just need to be elliptic, uniformly elliptic, p epsilon xi, xj, xi equals to minus divergence of f. Because it's in divergent form, then we typically write this way in U. And phi epsilon equals to g on the boundary. So if there's no scale epsilon here, then this is just a normal problem that you can use Calderon-Zygmunt theory, right? Because Calderon-Zygmunt theory, in this case, divergent form, you have W1P estimates. And Calderon-Zygmunt theory typically tells you, again, if there's no scale epsilon, then typically you would have this estimate, C epsilon, times F in W, F in LP, I'm sorry. F in LP plus G in W1P. So this is a very basic Calderon-Zygmunt estimate, okay? But it's depending on epsilon. So what's really an important contributions of Avellaneda and Lin is that they prove that this C is not C epsilon, but C, this is independent of epsilon. Okay? So no matter how Aij oscillates like crazy, just provided that it's uniformly elliptic, then you have this estimate. And once you have this estimate, then we can plug in. There's a bit of technicalities here that I wrote it down here. I'm going to skip it. That we can apply it. The uniform estimate of Avellaneda and Lin to prove the result. So we can prove that for the boundary corrector, again, we didn't do homogenizations, but we get that the estimate is W1P is less than C times epsilon to the power 1 over P. And I think that I don't remember what's that, but in section 4.2, in the paper with Sprackle myself, we give example to show that this epsilon to the power 1 over P is optimal. So we came up with some examples showing that this is exactly the correct rate. So although that we applied the black box, the very important estimate of Avellaneda and Lin in a very abstract way, but it turns out that is that. Okay, then so as I said, I'm just highlighting the steps here because I'm nearly done. So to prove the W1P results and stuff like that, then we just need to take these correctors into account. And, so in other words, to do W1P, so earlier for L infinity, what we needed to do was just take U epsilon minus or plus 2 epsilon W epsilon plus epsilon square of V of X over epsilon D square of U epsilon. That's for L infinity. For W1P, we really need to also take this boundary corrector into account. Minus, I'm sorry. Yeah, for me at this moment, minus and plus are kind of the same. So forgive me if I'm making a sign mistakes here. Yeah, so we really need to take this sort of boundary corrector into account in order to capture it. Okay, and then what is important is that we can use finite element methods to check that all the rates obtained are optimal. And I didn't do any of the numerical results. That's all what Timo did. So let me conclude by saying that you know, I believe that the BJ that was obtained almost more than 30 years ago, actually. BJ was observed 30 years ago here, was a natural object, right? But it's only BJ. And if I go back here, if you have a look, blah blah blah, where is it? Okay, so that's BJ is exactly this terms here, B here, right? So if BJ was 0, then we would have that is it's a C-good matrix, right? But in general, it's not 0. And therefore, let me go down finally, is that, yeah, so let me write here so that I'm not, so BJ that was defined by Avellaneda and Lin is Aij, Y, Ry, Yi, right? Repeated in I. And if BJ is always 0, then we have A is C good. But in general, no. And then CKLJA is equals to the integral in the torus of minus of AIJY RY YI VKLY dy. Okay, and if we write it also in the framework by using this notion of BJ, it's going to be BJY VKLY dy. Okay, so to understand when this one is 0 or not is quite complicated, because it's another level of complications with the corrector problem. But I guess that is a good way to go, because there's so many hidden structure there. And yeah, I believe that yeah, there needs some fresh minds and, you know, new ideas from the younger people here, I guess, to try to figure out what's hidden, what's missing, and understanding this will help more to understand the perforated domains, the almost periodic setting, or the random setting. What are the analogs of these objects there? And even in the periodic setting, I believe that understanding this will have to understand further hidden structure. Or maybe I'm wrong, I don't know. But let me stop here for questions or concerns.